we can see from the formula we've arrived at for the fraction that it's in fact a quotient. So when we compute its derivative, we may use the quotient rule. Sometimes the quotient rule is not very convenient and leads to very long and ugly expressions. So there's actually an alternative in this case, which is to expand the numerator and to divide through by the denominator. Now here I've done that, and let's see what this simplifies to. So in fact, this can be rewritten as 1 minus, the leading term of this will be 1, the next term will be 2d r and r squared, so there'll be a single r remaining in the denominator, and finally the last term will be minus d squared over r squared. So what have we done here? We've subtracted away the two terms that cancel each other, and we've been left with two terms alone, and now we're ready to take the derivative. So we've seen that this function of the radius can actually be written in a slightly simpler form. It's going to be advantageous to simplify this even further to the form of power functions, since those are very easy to differentiate. So this can be written as follows, and we can now easily compute the derivative of this expression, remembering that capital R depends on time. And so what we obtain is 2d. Here's a power function. We're going to have a minus 1 come out, and we'll be left with r to the minus 2 multiplied by dr dt, according to the chain rule, since r depends on time. Here, the constant d squared comes out. Now, r to the minus 2, when we differentiate this, we'll get r to the minus 3. A minus 2 will come out, turning this to a plus and putting a 2 down here. Now also, we have a chain rule applicable to this term, and so we have dr dt appearing here as well. Let's group together terms and take out a common factor. We see that there's a common factor of 2, a common factor of d, and a common factor of capital R squared that we can take out, as well as dr dt. And when we take out those common factors, let's see what remains. There's a minus sign here. And here we have one factor of d that remains, and one factor of capital R that remains. Now let's use the information that we were given in the problem. So let's go ahead and substitute in here. We're given that R at the instant of interest is 5 times d, and so this will be 2d divided by 5 squared, which is 25, multiplied by d squared. We can do a cancellation here. dr dt is a, as we're told up here. And here we've got a negative 1 plus d over 5d. Remember, we were using this information, so this reduces to 1 over 5. We can rewrite this as minus 5 over 5. So altogether, the term in square brackets will be negative 4/5. After simplifying this result, we obtain this quantity, which in fact works out to be minus 8a over 125d. And so all in all, we see that the fraction of living tissue in the tree will decrease as the tree grows, and the rate at which that happens depends on how quickly the trunk grows in width, as well as the fixed constant thickness of that living tissue.